Last time we discussed linear reconciliations of order 2, 3, and what do we need to do if we have non-homogeneous elements in this relation. And today I want to start with another type of recurrences. So it is good if you have linear recurrence relations, but in some cases you don't have this type of relations when you can write the explicit formula from it. And so example of such sequences of Catalan numbers. Do you know any definition of Catalan numbers? No? No. Okay. So there are plenty of them, about, I don't know, 10, 15 different types of definitions of Catalan numbers. And I will, so firstly, I will give you some different types of definitions, and we will discuss why are they is it the same are the same numbers. So I give you, maybe four different definitions. First is the number of different triangularizations of the convex n polygon. So I take n polygon, and then I try to provide the triangularizations using the diagonals, non-intersecting diagonals. So for example, if I have triangle, then each is a unique triangularization. If I have square, I will have two different triangularizations. And if, for example, for pentagon, I need to somehow choose the non-intersecting diagonals such that all parts will be triangles. This one and this one. The number of triangles. We can take regular So we start with 1, then 2, then 5. Okay. B is the number of, so I have grid on the plane, and I want to connect the points 0, 0, and n, going only up and right, such that this path will go over the diagonal. Maybe I will get it. So I start from here, going to here. And I want to go, so go only up and right and over the diagonal. Which color is not visible? Red or green? Nothing. Okay, I will give you, so for example, if I need to go from okay, blue. Don't know. So I want to go over the diagonal. So I have only this path and this path. So I have only two options here. And if I'm going from 0, 0 to 1, 1, there's only one way to do this over the diagonal. And if you have so maybe I will correct this picture, delete additional row from this picture, and I'll show you that there are exactly 5 different ways of doing this. So this is this one, this one, this one, this one, and this one. So this is green, and I don't know if you can see anything on this picture. So you can go this, and this one. So it's exactly, again, it starts from 1, 2, and 5.
So we should first go up.
First, always go up, because you need, so all paths should be over the diagonal. So you can go right here, because it will be under the diagonal. I need to be always over the diagonal. So I need to write the definition. All paths from 0, 0 to n going up and right over the above the diagonal. The next definition, I should put it here. Is I want to the number of expressions of 2n brackets, but I mean that, so I want to write 2n brackets, n left one and n right one, such that they given logical expression. For me, I mean that for each open bracket there is corresponding closed bracket. So for example, if I have 2 brackets, I can give you this sequence of brackets, and if it's 4 brackets, I can give you these sequences. So for each open bracket there is corresponding closing brackets. You can imagine that I write the product of n different numbers, and I want to but I want to calculate how many different type of pairwise product can I take to count the whole product. So I can, firstly I can, so for example, if I want to n. So for example, if I want to count the product of this expression, I can firstly count the product of these two guys, then these two, then these two. Okay, so exactly n plus 1, yes? N plus 1. So for example, if I have 3 elements, I can count this way or this way. So I can calculate the product using. So if I know how to calculate the product of 2 elements, then I can calculate the product of 3 elements in 2 different ways. Okay, so for 3 brackets, there will be like this one, this one, this one, this one, and this one. Okay, again, it starts from 1, 2, and 5. And similarly, you can just, I can give another definition. I just write the sequence of plus and minus ones. So I have n plus ones, n minus ones, and I write the sequences of plus 1 and minus 1 such that the first k summoned is always non-negative. It is the same. So, for example, if I can say this is the same as previous definition, because I can assign to all open brackets plus 1, for closing brackets minus 1, and the property that they are corresponding to each other means exactly that the sum of first k is always non-negative, because if it is negative, it means that on some step I have more closing brackets than open brackets, and this is wrong. So I cannot. So there can be such situations where I have closing brackets more than open. But if some of the first k elements is non-negative, then it means that for each open bracket there exists corresponding closing brackets. Because, for example, for the first, so the sum of all elements is 0. So there exists k, minimal k, such that this sum will be equal to 0, and this means that it will be corresponding bracket to the first bracket. And so if I know where the first bracket is ending, then I can calculate what is happening to the other brackets inside this and outside is first bracket. Okay? And maybe I will give another definition. Well, there are plenty of them. So, for example, I can, okay, for maybe from the graph series, it is the number of binary trees. The number of binary trees. So you know what the tree is, yes? And so you can, binary means that you start from root, and then you go, so we have only 2 edges going from root. And so, for example, if you have, I know how to call it, depths or height. Height 1, you have this tree. If you have first, you can do these two pictures. So you in each vertex, I have two edges going down or 0. And for the 5 vertices, I will have this picture, this picture, this picture, this picture, and so if I want to correspond with the previous one, I should write something like the number of binary trees with n leaves. So here I have so if you have 2 leaves, you have 1, 3 leaves, we have 2, and for 4 leaves, I will have 5 different kind of binary trees. And actually, there are a lot of more different definitions of Catalan numbers, but I think we'll stop here. Actually, firstly, I want to prove that they are all equivalent to each other. So the number of triangularizations is same as all paths, the same as different type of bracketing, and the number of binary trees. So I want to prove that I can denote it, but so maybe with some shifts. So for example, if I take the AN as a number of n polygons, BN is number of paths, CN is number of put into in brackets, and the n is number of binary trees. That will be something like AN minus 2 is equal to BN is equal to CN is equal to DN minus 1. Because for the triangle, I have n equal to 3, and this is the first case. For this, I will have Bn, B1 will be 1, C1 will be 1, and here D2 will be 1. So I think that this equality holds. Okay, some of them is I think trivial. Can you see what could you see which equivalence of this definition is true? I think it is easy to prove that Bn is equal to Cn, yes? So why Bn is equal to Cn? Can someone explain? So why the number of this path is equal to number of put in brackets? It's the number of sequences of the bracket.
I think for every, the reason that they're equal, because for every up action we take, we have to also take a right action, a right move. For every up move has to have one, every up move has to have one right move also.
Yeah, Masoud is right. So we can, if we're looking at the path from 0, 0 to n, we can write this as the sequences of going up and right.
Yeah.
And there will be exactly to n steps. So n steps will be up, n steps will be right, and there will always more steps up than right. Because if the number, so if I'm going, if I'm looking on the first k elements of the sequences, then the number of paths to the right should be less or equal than number of steps to the up, because otherwise I will go under the diagonal. So first step should be must be the step up, and for example, I cannot go up and right, because that means that I will be under the diagonal. And this is exactly the number of sequences of plus and minus ones. So I can correspond, so I have a bijection between the path from 0, 0 to n and the sequences of plus and minus ones such that the sum of the first chi elements is non-negative. Okay? Okay, so maybe I should write something. So Bn is equal to Cn, and the proof is that, so the path from 0, 0 to Nn is one-to-one correspondence with sequences of steps up and right. Such that for each k in there are more or equal steps up than steps right into the first k elements. And this is the same as the sequences of plus and minus 1, such that the sum of first k for all k, the sum of first k elements is non-negative. So there are more plus ones than minus ones here. Okay. What about binary trees? Sorry?
Why do you use the n minus?
I denoted by the n the number of binary trees with n leaves, and so here I have 2 leaves, and there will be only one such binary tree. For 3 leaves, there will be 2. But I know I can denote it by the number of vertices. Then I should write more. So if I have for n vertices, I need to so I need to provide some calculation. So for 3 vertices, so here will be 3 vertices and 1. This we have 5 vertices and 2. So I need to 7 vertices and 3. So I need to divide by, so if I have 2n plus 1 vertices, then I will have number n. So I need to calculate n divided by 2 and minus 1, something like that.
If we cut one line in the polygons, it will be like this crazy picture.
Yeah, but how do you? But okay, but how do you describe? So, for example, if you take this binary tree, which triangulation will you correspond it to? Could you explain it? How do you provide the diagonals? I think it is simply to say that it is the same as brackets or path from 0, 0 to n. So for example, here the number of edges will be exactly the same as the number of brackets. So maybe I can provide an algorithm how to reconstruct the positioning of brackets from the picture of binary tree.
So, for example, the first one, we have 7 brackets.
Yes.
First brackets would be the big brackets. And yeah, the first 2 would be the big brackets, and each pair it would be the smaller brackets.
So I think is this correspondence.
Yes.
Uh,
The rest would be also similar. We have wait a minute. Yes, yes, we have. Yeah, we have one blank.
this one.
No,
No.
no. It would be 2 inside each other and 1 alone.
Okay. This one. Okay.
And
Okay. This one will be
no.
okay.
And we have inside it 1.
Do you understand the algorithm, or you just try to suggest how do we do the projection? Okay, maybe it's not very simple, but I'll give you a hint. Let's firstly prove the recurrence relation in this number. So we just give the recurrence relations for this guy, and then if for this guy the recurrence relation will be the same, and we check that the first 2 elements of the first 2 elements are equal, then then we'll prove that Bn is equal to Dn minus 1. So first of all, let's give recurrence relation. And then it will help us to see where is the projection between Bn and Dn minus 1. Okay, how do we get the recurrence relation? So let's look at our sequences of brackets. This is Dn. We can see that this is a repetitive structure, yes? So, for example, the parts of this the subsequences of these brackets can be also the for example, I can so if I take, for example, these subsequences, we see that this is also the correct sequences of correct sequences of brackets. But how can we combine the structures? Let's look at the first open bracket. So we know that if it is the correct sequences, that somewhere here these brackets will be closing. And if it's closing, then somewhere closing, and all sequences, if you look sequences inside this bracket and the sequences outside this bracket, it will be the correct sequences of brackets in terms of for each open brackets inside of these red brackets, there will be corresponding closing brackets. In terms of paths, I can look at the first time my path intersects the diagonal. So maybe it will be intersecting the diagonal at the last point, maybe in the previous point, maybe in the first point. But then my path will be divided into two parts. Each of these parts will be passed from 0, 0 to mm, and from mm to nn over the diagonal. So I can write this picture here. So if I take any path from 0, 0 to nn, then I can look at the first time this path will be intersecting the diagonal. So it starts from here. Maybe I will change the color. So it starts from here, and somewhere will be the first time it will be intersecting the diagonal, and then I can look at something like this path, and this, and they will be also the path from 0, 0 to nn over the diagonal. So this will be the, so here we can meet all types of paths from mm to nn, and here I need to shift this diagonal because I take the first intersection. Then this path will be go strictly above the diagonal. So I need here to shift it a little bit and go and look at this diagonal. And then, so I want to go from points 1, 1 to 1, 0, 1 to here we'll have m minus 1 m. And there will be, so all the path that starts from 0, 0 and goes to an m and not intersecting this diagonal should go above this diagonal. So I can divide my path into two parts. First part will be the path from mm to nn, and second will be path from 0, 1 to m minus 1 m. Okay. So the number of how many? So can you tell how many of the sequences we will have if so we have n brackets total, and for example we have k brackets here and n minus k minus 1 brackets here. How many possible sequences of brackets do we have here? If here we have k brackets and here we have n minus k minus 1 brackets.
Excuse me, we don't count the red middle bracket.
So we take the first red bracket. It can end anywhere, but inside of it we will have k brackets, for example, and outside we will have n minus k minus 1 brackets. So in this type of situation, in this kind of situation, how many possible correct sequences of brackets do we have? Do you understand the question? No. So I can write an example. For example, for 3 brackets, we have the following situation. So these are the sequences where the brackets ends in the beginning. So here k is 0, here n is equal to 3, and n minus k minus 1 is 2. The first brackets can end here, and here with the only one possible situation, k equal 1, n minus k minus 1 equal to 1. And here we'll have two possible situations, and this means that k is equal 2 and n minus k minus 1 is 0. So I divide all sequences into different types of where the first bracket ends. So if it ends here, so if it ends here, this is the first one. If it has one bracket inside, is this one, and if it has two brackets inside, this one. So how many possible can we calculate the number of this type of positioning of two end brackets, this type of position of two end brackets, and this type of position of two end brackets? No? So, for example, here inside, I will have again the correct sequences of brackets. Yes, correct sequences of brackets. How many are there correct sequences of brackets? C2, yes. And outside is C0. Here I'll have one bracket inside, so there are C1 sequences of such brackets, and here I have also C1. And here I have C0 here and C2 here. Yes? Okay, so for example, this type, I have one big brackets where the first open and the first closing brackets, the corresponding closing brackets of the first one. Inside I have the sequences of two brackets. The number of sequences of two brackets with correct positioning is C1 by definition. So here I have this C1 number of such positioning of brackets. And outside I have again, I will have the two brackets with the correct sequences of two brackets. So I have again C1 here. Okay? So if I want to calculate the number of such brackets, do I need to summarize, multiplicate it? And what should I write here as formula? So can we write the formula for the Tn? Do you understand the question? No? So, for example, in arbitrary situation, I see where the first bracket ends, and I want to calculate. So inside I have k correctly matched brackets here. And outside I'll have n minus k minus 1 correctly matched brackets here. So by definition, I will have that this should be ck, the number of correctly matched brackets here. And outside I will have Tn minus k minus 1. Such sequences of correctly matched brackets. So for each correctly matched brackets of inside, I will have the corresponding brackets outside. So this means that I need to take the product of these two guys. Yes, and then I just need to summarize it. So for example, here, if I want to calculate C3, I need to write the following formula: C0 times C2 plus C1 times C1 plus C2 times C0. And so if you put C0 is equal to 1, then we will have, we can calculate, and this will be 2 plus 2 plus 1, exactly 5, which is correct because C3 is equal to 5. So we can just check that our calculation is correct. And so for the Cn, I will have C0 times Cn minus 1 plus Cn times Cn minus 2 plus etc. plus Cn minus 2 times C0. So we have recurrence relation, but it's tricky in two senses. First of all, it is not linear. It is some kind of quadratic relations because I have so my nth element depends on the product of sum of product of previous elements. And the second remark that I need to calculate all previous elements. So in linear recurrence relations, we always have that nth element depends only on fixed number of previous elements, 2, 3, and now we need to count all the previous elements to count the nth element. So this is some kind of tricky recurrence relation. But if you understand this idea, maybe now it's easier to see what happens with the binary trees. So if we look at binary trees, maybe you can see maybe we cannot see the bijection, but we can prove the recurrence relations, the same recurrence relations, the same idea that we look at where so we want to divide this picture. So if we need to see the same idea, we need to divide these trees into two binary trees. And if we calculate the number of binary trees of these two separate parts, then we can calculate the recurrence relation. I can maybe draw some. Yes.
The case of 3 pairs, right?
Yes. Sorry?
3 pairs.
Yes.
What is it included now?
Okay, so we have 3 independent pairs of brackets. I look at the first open bracket and see where is the corresponding closing brackets. Yes? So it can end it right here, right after this open bracket, after the one pair of brackets, and after the 2 pairs of brackets. So that I have all sequences of correctly matched brackets are now partitioned into 3 different cases. So this3 is equal to number of these types of correctly matched brackets, this type of correctly matched brackets, and this type of correctly matched brackets. Okay? And now I need to count them separately. So in each of these, I have the correctly matched sequences inside this bracket and outside this bracket. So I just write this 3 is C0 times C2 in this case, C1 times C1 in this case, and C2 times C0 in this case. Yeah, what was the?
What is K and what is we have K.
Yeah, so we have n equal to 3 and k equal to 0. So n minus k minus 1 is 2. Here?
Down.
Yeah.
Down. Yeah, here.
Yeah, what n equal to 3?
No, I like this.
Yes. Yes.
What is K?
K, in these two cases, K is equal to 0 because inside this bracket is no one. So here again, K is 0.
There is no correct
Yeah.
sequence.
So I look at this one and this one. So this is correctly matched bracket, and inside this one also, yes. Here is C0. There is no brackets here, and here is C2. I know. So I have two different types of positioning of two opening and two closing brackets. This one and this one. This is C2. Okay.
Professor,
Yes.
you need the numbers of the leaves for the tree, or the number of nodes?
Yeah, but I want to see, you see from, so I think that you can look at this picture and see the same pattern as I describe you when it proves the recurrence relations. So again, I can just look at this picture and try to find how can I partition these trees into different types such that they have repetitive structure. I don't know how to say it. So how can we divide these binary trees into some smaller trees? Where can we? So I want to find the analog of this first opening and closing brackets here.
I think, Professor, I think we can manner it with the first two leaves. I mean, the first node. If other nodes are connected to the, for example, left-hand side of the first node leaf, then it means that it means the K is not equal to 0, and it is equal to the number of.
The first node leaf, you mean the left one?
The left one,
yes.
Or
you mean the root, or you mean the?
No. I mean the root, the left leaf of the root. If all of the.
So this one.
If all of the yes.
Yes.
The leaf, I mean. Yeah, exactly.
This
Yes.
This
Yeah.
one.
No. Yes. That's sorry. That was great.
Okay.
And then if all of the other nodes are connected to this node, then we can consider K as equal to n minus 1, I think. And then I think, is it correct or?
I think it's similar to the
arrows from up and the right.
Yeah, you can just look at the root and take this first edges from the root and then cut it from the tree. So if you look at the this root and two edges outside of this vertex, then our tree will be divided into two trees. Yes, so we will have left one and right one. And
yes.
So if so I just need to calculate how many leaves here and how many leaves I have here. So here we have 3 leaves and 0, 3, 0, 2 and 2, 0, 3, and 0, 3. And you see that in each branch, I will have the same pattern. So this is just have two cases because here I have two cases. Again, here I have two cases because here I have two different types of binary trees. And these are only one possible situation because here I have only one possible situation. And so again, I have the same idea. If I look at the first, so I have a root and the edges outside the root, our tree will be partitioned into two different branches. And I just need to calculate how many possible types of binary trees with the less the number of leaves. So you see this. So you see this correspondence because, so for example, so this is corresponding to the situation when the first brackets end right here, and now I need to write all the brackets outside here. This situation is corresponding to the type of situations where the opening and closing brackets, so the all tree will be inside the first bracket, so it's all in the left part of the tree. And this,
K equal to 3,
type,
right?
This type is corresponding to a situation where the left tree will be inside those brackets and right tree is outside the brackets. Okay? Do you see correspondence? No? So I can prove that I will have the same recurrence relations in this situation and in this situation, and the proof is just the same because I say that I take the root, I take the two edges, then I cut these two edges from the tree. Then I will have two branches. One will have k leaves. So in arbitrary situation, when I will cut the root and the two edges outside from the tree, then I will have two branches, one with k leaves. The other will be with n minus k leaves. And the number of such trees is dk times dn minus k. But I need to be careful because it will happen if k goes from 1 to n minus 1, because there is also type of situation where I have leaf here, and so I need to write something like, so the formula will be something like dn is equal to so this will be dn minus 1 plus dn minus 2 times d2 plus etc. plus d2 times dn minus 2 plus dn minus 1. But I can always write this d1 or something like this. And so now if you, so I have the same correspondence, but I need to write, so if I denote this dn, like if I need to prove that dn minus 1 is cn, then I can just write this in terms of cn, and I have the same sequence them recurrence relations as here. So I can write this as n plus 1 is cn times no.
Sorry, we started C from 0 for previous one. Should we start it from 1 again? Same thing in
Yeah.
the right table.
If I just put dn minus 1 as cn, then I will have the same correspondence here. That's the following correspondence here. Cn minus 1 is equal to Cn minus 2 times C0 plus Cn minus 3 times C1 plus etc. plus C0 times Cn minus 2. And this is the same as my recurrence relation if I put n minus 1 instead of n. here. So this is the same. Okay? Do I need to be more, maybe say some words about proof again? Or do you understand what happened here? So I just want to show that the idea is the same, because I just divide, so all possible situations, I just cut out this root, and then I will have two binary trees on the left side and on the right side, and just this I just need to provide a accurate calculation. But so it's not very straightforward, because it's not very so because here I will, so the algorithm of going from brackets to the trees and to the other hand is that I put, so if I go left, I put something inside, and if I go right, I put something outside. This is the same idea. So for example, if I go, so for example, if I look at the first bracket, so if something is outside, then I go right here. And again, if something outside, then I go right again. Here I start with this guy. If something outside, I go right. And if something inside, I go left. Here I have one inside and one outside. So I go one left and one right. And here all game is going inside the bracket, so I go left. And now if they're separate, I go left and right. And if they're inside, I go left and left. So I go from up to down, and then if I want to decide going to left and to the right, I just look at the, is it going separately or together? So all that coming into the first bracket going, so I would, so if I start from this bracket, then I go to the inside, and I see where this bracket is closed. And so all that is going inside is going to the left, and those outside go to the right. Okay, I think we'll have a break now. And after that, we'll prove that it is the same as, you can think it in this break why this equivalence to the number of triangulation of polygon. And after that, we will prove the formula. Actually, we will prove the formula for the number of Cn. I think in 2 or 3 weeks after that, because so in the next lecture we're going to discuss formal power series, another instrument helping us to find some relations and properties of sequences. And I will give you another proof of finding the formula for the Cn using this relation. So actually we can use this relation to find the formula for the Cn. But today we will have some tricky way of doing this using some geometry. So we'll use geometry to just find the formula for the Cn. Okay, so I think we'll have a 15 minutes break. I will give you a hint. It's not very important. I think you can see. Okay. If you want to calculate this one, so what's the idea? So firstly, we calculate this. This guy is 2 to the power n. Then we calculate the alternated sum. Yes, it was mostly 0 and 1 if except n equal to 0.
If
Yes.
we start n1, it will be 0, right? Not n0. Just n1 minus n2, n2 will be always 0.
Sorry?
If we start n choose 1 from
Yes, we start here or here.
there, the second.
In second one, if you start from n choose 1, then the answer will be 1 because it is minus this one. This one is 1, but then, so this one is minus, no, it will be n choose 0, this is 1. Okay, so here we have the root of polynomial. So you have the root of degree 1 from the 1. Here 1 is 1 is the root of degree 2. So if you want to calculate this one, you need to go and calculate the roots of degree 3. I don't know if I'm saying correctly. So you take complex space. Here we have 1. And if you know how to see the roots of 1 of degree 3, we have exactly 3 roots. Here we have these two guys. I can define it by omega and omega squared. And then I can do the same. So if I write this is to the power n, then I can write this to sum with omega squared, and so on. And this will be 1 plus omega to the power n. Then I can write this with the omega squared. This is 1 plus omega squared to the power n. And then if I summarize it, then all these guys will be vanished because 1 plus omega squared is 0, and 1 plus omega squared plus omega in the first power is 0. But the only guys that will be not cancelled will be these guys. And so the idea is just using, so if I need to calculate the force, each force of the binomial coefficients, then I need to go to the root of the degree 4 and so on. So it is not a very easy idea, but it is the same idea as here. So I want to write some, so I want to use the formula for the 1 plus x to the power n, and I want to take different x's such that I can cancel all the binomial coefficients that I don't need in my sum. And so this is the idea. Okay, if you want, we can discuss it into some part of lecture now, or if we can ask in Telegram. Pascal triangle. So first idea is try to manipulate with the binomial formula. So if you care only about odd and even rows, you just, I don't know if you have number theory course, but you can just take all coefficients modulo 2, because all you need, so all you care about is you have 0 or 1 modulo 2. So you can just try to, so for example, if you take 1 plus x squared, so if I have this mod 2, it's the same as 1 plus x squared, because 2x is 0, for example. And if you know, so for example, if you modulo 2, always I can write a plus b is a squared. So you just take this formula and also like this formula, I think, because the same holds here, because I can just take the squares and fourth powers and sixth power, and this will be the same. And if you know this equality, then you can expand the 1 plus x to the power n and find where we'll have, so when this is 2. not this, but we, when we'll have this when this is true. I think you can use this equality to prove it. And the second idea is just, well, sorry, second idea is just look at the Pascal triangle. So you see that you start, so you have like, but you write only zeros and ones here, because all you care about is even or odd numbers. And so, sorry. So, yeah, it will be. So if you write this, you can see. So if you write this triangle, you can see pattern here and prove it.
Yeah,
But
we saw the pattern, but how to, we have 2n plus 1 for n start from b.
okay, so idea is that I can, so if you see the pattern, you can prove it. And okay, if you have a problem with how to write the proof, we can discuss it privately. Okay? Okay? Okay. Okay, so we stopped at the triangulation of polygon, returning to the Catalan numbers. So we have polygon, and again, I want to see the same idea as in previous cases, where I trying to describe my number of triangularizations into number of triangularizations of some parts of this polygon. And so I need to divide my polygon into two smaller polygons and calculate the number of triangularizations of smaller polygons. And actually, so we can start from the two different ideas. The first idea is to look at the, so first idea is to look, for example, so fix one of the vertices, and then look at the edges or diagonals from this point. But its idea can somehow, in some cases, there are no diagonals using this point. So we cannot describe the triangularizations of polygon in terms of triangulation of smaller polygons, because there are no, so I cannot divide this into two polygons using this point, because there are no diagonals of using it. And so if we cannot use the point here, we can just took one of the edges. Let's look, let's pick one of the edges, fix one of the edges. In how many triangles does this edge belong? So how many triangles have this edge inside it in triangularization? How many? How many triangles in triangularization will have this edge?
6.
I asked how many triangles of triangularization will have this edge inside of it?
6.
6 triangles?
Yes.
So so for example, if I draw the pentagon and choose the triangularization, then this edge is belonging to exactly one triangle. Yes? Yes. You said So how many triangles can I provide using this edge? Maybe I don't know what you ask, what question you are answering.
Like we meant that after we like that. The one that is like
So this edge belongs exactly to the one triangle in triangulation, yes? So if you have the triangulation, we have exactly one triangle will have this edge inside. And so we have two smaller polygons into my triangulation. And now I can calculate the number of triangulation of this guy and number of triangulation of this guy and multiply it. And I just need to look at all possible vertices of this triangle and summarize all possible kind of triangulation. So for example, if I look at the pentagon, then so I have my red edge here, and and so I have two triangulation with this triangle, one triangulation with the middle triangle, and two triangulations with the left triangle. And so if I choose the edge, and then I choose the third vertex of my triangle, which has this edge in the triangulation. And so this vertex can be any of these vertices. And for each of these vertices, so here I will have exactly two possible triangulations because I have two possible triangulation of the square. Here I'll have exactly one triangulation because I have only one triangulation of triangle and one triangulation of triangle. Here I'll have again two possible triangulation of a square. So again, I just need to write the formula. So if I denote by an the number of triangulations, so for example, this vertex will be n minus 1 and n, and here I'll have 1, 2, 3, etc. n minus 2. So for each of these n minus 2 vertices, I will have here the triangle, and then I will have one smaller polygon to the right hand side and one smaller polygon to the left hand side. And so if this vertex is number k, then I will have k plus 1 polygon here, and here we'll have from k to n minus 1, n minus k vertex here, n minus k polygon here. So an is equal to sum of a k plus 1 times a n minus k from k from 1 to n minus 2. So for example, if I take a 5 I will have a A2 times A3 plus a so maybe I need to if I count correctly, n minus. So here maybe we have n minus k plus 1 from no. A2 times 3 plus S3 times K1, A4, okay. Yes. So this is for K equal to 1, this is for K equal to 2, this is K is equal to 3. And so I'll have the same formula, but I need to shift it to the n minus 2. So if I want to prove that Cn is a n minus 2, then again I need to just write this in terms of Cn and check that this is the correct formula. This is the same recurrence relation as in Catalan number. Do you need to repeat this? It's okay? Or is it hard to understand? Okay.
Could you please explain it once again?
Sorry?
Could you explain it once again?
Yeah, okay. So I fixed one of the edges, and then I look at the triangle in my triangulization that has this edge inside of it. So I need to choose the third vertex of this triangle. This third vertex can be any of the other vertices of my n polygon. And so for each of these vertices, my triangulation will be divided into two parts, one of the left-hand side, one of the right-hand side. And so if I want to, for example, calculate the number of triangulations which have the triangle of n minus 1, n and k vertices inside of it, then I just need to calculate the number of triangulations of this polygon to the left-hand side and this polygon to the right-hand side. So here, to the right-hand side, I have k plus 1 polygon, and to the left, I have n minus k polygon. So the number of such triangulations will be a k plus 1 times a n minus k. And then I need to summarize it over all different type of third vertices from 1 to n minus 2. So in this example, I have 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. I have exactly two triangulations with vertex 1, one triangulation with vertex 2, and two triangulations with vertex 3 here. Because here I'll have 0 polygon, exactly 2 polygon to the right hand side and 4 polygon to the left hand side. Here the same. Here I'll have triangles to the left and right, and here I have 0 polygon, 2 polygon to the right, and 4 polygon to the 2 polygon to the left, and 4 polygon to the right. And that just I need to summarize and check the multiplication formula. Okay. And so it's for this sequence, it's easy to prove the recurrence relations and to see how we can write the corresponding brackets. Because if I need to write a bracket, so I just look at the where the first bracket is closed is showing where is this triangle is going, and it's not. So I need to enumerate all the edges and then look edge after edge where the third vertex is, and then places my brackets. But it's not very easy. It's easier, I think, to understand this formula. So we just dissect into two triangles and calculate the number of triangulation here. Okay. Questions? I doubt if you have time to prove the formula because I need like 20 minutes, but we don't have 20 minutes right now. But let me ask you, so you don't have, so you didn't discuss any formal power series in the previous course, yes? Formal power series.
Formal or series?
Formal, okay. Power series? No. Series? No.
No.
Formal power series. What is formal power series? We have, so right now we try to analyze the sequences and try to find if we can, so we have in combinatorics, we often have some series of numbers, and we want to find the explicit formula or just the behaving of this an, or upper bound to lower bound for the an. And one of way of looking at this is looking not at the sequences, but on the some function of it. So, for example, we can look at so-called formal power series. It's just the polynomial with the infinite powers here. I don't think that you were working with this before. Yes. But I understand that you are familiar with the concept of polynomials, and you know how to summarize polynomials and multiplicate polynomials. But this is just the same, but we have problem because we have infinite elements here, non-zero elements. But the idea is often the same. So if I want to multiplicate it. Multiplication is only depends on the first n elements, so I can just if my sequence is not very hard, I can just calculate the explicit. So I can calculate the multiplication of my polynomials, and of course you meet this power series when you discuss Taylor series maybe. So you know what. So for example, you know what this infinite, so the sum of geometric progression, infinite geometric progression is, and so for example, why is it useful to use? Why is it useful to look at the formal power series? For example, so I want to just maybe. I wanted to maybe see the whole idea, and then it will be easier to understand what we're doing. So if for example, I look at the formal power series where an is equal to cn, then this formula, this recurrence relation of Catalan numbers is similar to the multiplication of polynomials. So if I if I look at this function, formal power series actually, and try to multiply it by itself, you can just assume that we look at the first n coefficients and try to multiply them. Then how can I calculate this one? So I will have C0 times C0 is a term without x. Then I will have x times C1 C0 plus C0 C1. Then I will have C2 C0 plus C1 C1 plus C0 C2 times x squared. x squared. So this is C2, this is C3, this is C1. So if you multiply it by itself, we'll have the similar power series, but shifted to the 1 power. So I just can write this equation. So fx times fx will be equal to so if I multiply it by x, then I will have fx minus 1. So this strangely looking recurrence relation have this beautiful short equation on the formal power series. So I just take f of x minus 1, and then I take x squared. So I need just to try to solve the quadratic equation in terms of formal power series. I need to find what are the formal power series will be solution to this equation.
Excuse me.
Yeah.
Why did you multiply x times
Yeah,
f of x times f
because
of
here
x?
I have c1 plus c2 times x plus c times x squared, and here I have c0 plus c1 times x plus c2 times x squared. So I need to multiply it by x, so they will be the same power as in fx, because this is equal to this one except for c0. But I will repeat it into the, so this is our goal, but I think the next lecture will be just discussing the definitions and simple construction with the formal power series. And because if you need to solve this, you need to, so it is quadratic equation, so you need to find the discriminant, and if you want to calculate the discriminant, you need to calculate the square root of something like 1 minus 4x, and this is not so. Again, if you know Taylor series, you know how to write this formula. Yes, so you can take derivatives and you can write this formula for this guys, but it's not very easy. So we'll be so. I don't think we'll have enough time in the next lecture to discuss this one. So maybe in the end. But first of all, I want to prove the formula for the Cn, not using this technique. But after that, we'll return to this. Okay. Do you need a break? Small break? No? Okay. So we start now. Okay, but if I want to, I don't know how to do it better. Do I need to place file in the chat or Telegram, or just because I have PDF and I have printed some tasks in the paper and I have PDF. Where I can place PDF in Telegram is better.
I think Telegram is better.
Yeah. Okay.
Telegram.
Yeah. I could just I will provide it into the Telegram chat. Yeah. So please don't forget to write your name. It's integrated as always, but this so you cannot put a here and a here, yes, because it will be not the ring.
So they are not the same. They are the same.
They're the same. So you can put a here or here, B here, C here, and so on. So it is the same as arrangement.
So
Yes.
how many derivatives of this word are there?
Yes.
In other words, you can say how many permutations such that none of the letters stay in space.
Yeah, but this letters cannot change places because it's the same direction. Yes. So I want to calculate the number of permutations such that there are no so they're not the same letters in the same column. Yes. So for example, I can I gave QBC here, but I cannot.
This is nothing today.
Yeah, this is not a drain. Yes. So for example, if you have for A and B, the number of digits is 0. And for example, if you take AA and BC, then you need to take AA. So if you take ABC, you must take AA here, and there will be only 2 such derivatives. Okay. So you have 2 endpoints on the line. So, for example, you have 6 points, and you want to draw 3 arcs such that not have no common point. So, for example, I can write this one or this one. I don't know. So all possible types
Okay.
of vectors here. Yeah.
Thank you.
Okay.
Thank you.
Okay.
Sir, the question is there are how many ways to draw such picture, right?
Yeah. So how many arc diagrams can you draw? Yeah. So how many pictures? For example, if you have only 2 points, then you have only 1 picture. If you have 4 points, then you can have I think 3 pictures. This one and this one. And so the question is how many such pictures for arbitrary n. So for n, so n equal 1. So we have if 1 arc, you have 1 diagram. If you have 2 arcs, you have 3 diagrams. And for the 3 arcs, I just give you some cases, but it's not the all cases. I think there are more. Okay.
Okay.
Okay. So we have 15 minutes left to the end of the test.
Excuse me. For question number 3, you wrote a picture 1, 2, 3, 4, 5, 6, and 1 is connected to 4, 2 is connected to 3, and 5 is connected to 6. Is it the same as 1 connected to 2, 6 connected to 3, and then 4 connected to 5? Or we should consider it as...
No. You can write the arc diagram as just the sequences of numbers, the pairs of numbers. So like 1, 4, 2, 3, 5, 6, and it's not the same as 1, 2, 3, 6, and 4, 5. So this set must be the same. The set of pairs. You can assume that you have 2 n numbers, and you just dissect them by pairs and. Yeah. Sorry.
No. I need to explain for the third problem that I don't understand what is ABC. I understand it's a diagram we can turning to.
Yeah. So you have 2 endpoints here. For example, here you have 6 points. So you need to draw 3 arcs connecting this point. But they're not intersecting on this point. So you have like this arc, this and this arc. Also, so these are possible type of features of arc diagram. Yeah. Okay. So you draw 3 arcs, and they are not intersecting on the vertices. So you have each vertex belonging only to the one arc.
They intersect.
No, they don't intersect on the points. So each point belongs only to the one arc.
But we have to draw it.